Next paper will be fatigue behavior of single crystal nano-sized copper beams. Per Hanson will be presented it, and he is author of this paper.
Okay, thank you. The title of my talk today is Fatigue Behavior of Single Crystal Nano-Sized Copper Beams. And this work has been carried out at Lund University in Sweden. So the objectives of this work has been to study the sensitivity of small defects in nano-sized FCC single crystal copper beams under fatigue loading. And to do this, we have used displacement control loading. We have looked at 2 different temperatures to see the difference, how it impacts the results. We have looked at 3 different geometries for different defects. We have compared these different simulations regarding strain at plastic initiation and also strain at failure. And then we have compared the resistance to fatigue failure. And we also studied the plastic development in detail to try to understand what really happens inside the material. So this is a schematic, very simple schematic description of our geometry. We have 3 different geometries: a solid beam without any defects. We have a beam with an edge crack-like defects in the middle, and then we have a beam with a through the thickness void. All the beams have a square cross-section, and we load in the x direction. So in this direction. And this x direction corresponds to the 1, 0, 0 direction in the material. And here you can see some information about the size. It's quite small beams, around 100 unit cells of length. And the defects are 2 times 2 unit cells of size. So we have performed fatigue loading. We have a constant temperature, 2 different temperatures, 0.01 and 300 Kelvin, to see how that influences. As I mentioned before, we have displacement control loading. We have minimum displacement of 0 and then maximum displacement roughly 3 to 5 unit cells. So quite high strains in this case. To do these simulations, we have used molecular dynamics simulations. We have used a computer program called LAMPS. It's a classical molecular dynamics code. It's a freeware, so everyone can use it. In this code, we have used the EAM potential to describe the interaction between atoms. And this is a well-known potential for FCC crystals. And it contains 2 different parts. One has to do with the electron charge density, and one is a pairwise potential function. And then when we do the time integration, we have used a canonical ensemble, usually called NVT ensemble, where we keep the temperature constant to our 2 different values. And this is done by using a Nosey-Hoover thermostat in the simulations. So to evaluate our results, to look at the plasticity, we have used a measure that is called the centrosymmetry parameter. And this is a measure of the lattice disorder of the material. So it's a summation of the neighboring atoms, their positions. So these are vectors describing the positions of the surrounding atoms. And if this value is close to 0, that means that the structure is an ideal FCC structure. No plasticity or anything else has happened yet. But for higher values of this parameter, that means that we have found partial dislocation, stacking faults, and so on. And then for the really high value, that means that we have missing neighboring atoms. So that's at the surface or edge or corner atoms. And that's clearly seen in this picture here. This is the centrosymmetry parameter for the beam. And the color coding is this parameter. So the red ones here are at the edge and corner atoms. The green one is at the free surface. And the blue one in the middle, that's the ideal FCC structure in the bulk material, so to say. So we use a standard setup for the molecular dynamic simulations, nothing strange. We do a geometrical setup, then we do a relaxation to find the correct starting positions. Then we fix both ends of the beam, so it's like clamped ends. Then we apply a constant velocity to both ends of the beam, one in the positive direction and one in the negative. So we have a symmetric loading situation. And then we displace the ends of the beam until we reach the maximum displacement. Then, of course, we change the velocity the direction of the velocity and reverse the loading until we reach zero displacement. And we do this for up to 10 load cycles unless the beam breaks before that. So this is just some simulation parameters. I don't think we have to go through them. I've mentioned the most important ones. So now to the results. The first one here is strain at plastic initiation and rupture of the beams. And this is actually monotonic loading, not fatigue loading. So here we have the 6 different simulations with the different geometry and different temperatures. And here we have the different strains. This is strain at plastic initiation. This is a strain if the void collapses or closes. And we can see that this only occurs for one case. When we have a void, defect, and at high temperatures, then actually the void closes before the beam failures. And then this is the strain at failure. And you can see it's really high values that we get for these kind of single crystal materials. So if we now compare these as first, we can see that the case of a solid beam have the highest strain. So if we don't have any defect, we can withstand much, much higher strains than if we have a defect. So roughly in roughly 3 times the higher strains. If we now compare the lower temperature to the higher temperature, we can see that in all cases the strains gets lower when we increase the temperature. So we can withstand lower strains. And in some cases quite large difference. For instance, this solid beam, we only have half the strain at failure at the higher temperature. So now to the results of the fatigue simulations. So here we have plotted the average stress in the loading direction versus time for up to 10 load cycles. And this is the first figure here is for the solid beams without any defects. And so we have 4 different simulations, 1 at the lowest temperature and then 3 at the higher temperature. So we first look at the lower temperature, the red curve here. We can see that in the first load cycle we had very high stresses. And actually plasticity occurs here. We don't really see it, but it's this drop in the curve. And this leads to that in the following load cycles we had much, much lower peak stress in the load cycle. And we can see that we reach some kind of steady state. All the load cycle looks exactly the same. And this is because we have no evolution of plasticity in this case. So we would expect infinite life for this kind of beams. If you now compare to the higher temperatures instead, we start with the blue one, with the highest loads. We can see that we have some irregularities in the curve here. That's when we have a plasticity that starts to evolve. But here we can see different patterns. We can see that the maximum stress in each load cycle gets lower and lower. So this indicates that we have some kind of evolution of the plasticity in the beam during the cyclic loading. And actually it fails after 8 load cycles. If you now take the intermediate value, the black one, we can see it's the same pattern. High stresses in the first load cycle, then it gets lower and lower. It can withstand the fully 10 load cycles, but eventually this beam will probably break if we would have continued the loading. And then the one with the lowest applied load, we can see that we immediately reached its steady state and nothing really happens in the beam. So now to the case when we have a defect instead. We start with the case where we have a void, centrally placed void. We have here 3 different values of the applied load, and we have to use lower loads than for the solid beams, because otherwise it would break immediately in the first load cycle. So here we can see something strange. Quite early in the load cycle, we have a dip in the stress curve, and this is actually when the void closes due to plasticity. And then we have further events here, and we can see that in this first case, it actually breaks already after 3 load cycles. Then we decrease the load, not very much, but a small amount, and then we get a completely different behavior. We still have plasticity in the first load cycle, but then we reach a steady state and would expect infinite life in this case. And the same is true for the lowest value. Then we reach steady state immediately, and it looks the same in all load cycles. Then in the case of an edge crack, we have somewhat similar pattern for the highest loads here, the red one. We have lower and lower loads, but something strange really happens here in the second load cycle. I will show that later on in a short video. The beam almost breaks in the second load cycle, but it heals again, and we get the somewhat higher stresses again. So it can actually withstand 5 load cycles before it breaks. But it's barely, because it almost breaks after 2. The intermediate value here We see that the stresses go down. We have some kind of healing also in this case. But it can withstand 8 load cycles. And then for the lowest, we reach a steady state immediately. I would expect infinite life. So now I'm going to show you what really happens inside the material. So these are some events during the first load cycle to try to understand what happens, both for the solid beams, void case, and the edge defect. So we start with the solid beams here, and we look at the blue curve here. So the first picture here, this is a snapshot of the atomic positions and the center symmetry parameter. This is after relaxation, and this is at the first event that happens, this drop in the load curve. And this is when plasticity forms. So we have activation of a number of slip planes here in close back directions that we can see. And this continues until we reach maximum load, and then we start to push the beam together again, and we can see that the beam has been bent slightly. And this is because during the stretching it elongates, and then it's a very thin beam, so when we try to push it together it bends actually. Then we look at the case when we have a void. We can see this is the relaxed state. We have the small void in the middle. The first event that happens quite early in the load cycle here is that the void closes due to plasticity. Then we continue our loading and something new happened, and that's these new slip planes that has been formed. And more slip planes continue to evolve, so this is at maximum load. And then the last number of picture is for the edge crack-like defect. So this is after relaxation, and here we can see clearly that the beam isn't straight anymore. It's been bent up a little bit. And this is because this is not a symmetric case in this direction anymore. Then we apply our loading, and we have this step in the loading curve, and this has to do with plasticity that is forming. The difference is that in this case, the plasticity is quite located near the edge. It's not spread out over the entire beam like in the case of a void or a solid beam. And this holds true even at maximum load that we see here. And then the last picture is at minimum load, and we can see where you have quite a lot of bending and also some twisting of the beam actually. So now I'm going to show you some short movies if I have time. I think you have 2 minutes or something. So the first, this is for the solid beam. First with just elastic elongation. Then we can see that plasticity forms and we get these slip planes. And this evolution of the plasticity continues for the following load cycle. So more and more slip planes are activated. And the stress gets lower and lower. We can see that this part gets thinner and thinner, and we get necking and so on. And eventually it will break after 8 load cycles. Maybe we can go directly to the finish. So there it snaps off. The next one is for the case of a void. We could see that, take it from the beginning again. First just elastic elongation, and then almost immediately the void collapses due to plasticity. And we form these slip planes. But then we can see in the following load cycle nothing more happens. It looks exactly the same all the time. And that's also seen in this stress versus time plots, that nothing more happens. So in this case, no more damage happens. So we would expect infinite life after this first plasticity. Oh. And that's the last one. I don't know why it didn't start. With the edge defect, we can see that the plasticity is quite close to the defect, and we could see there that it almost broke after the second load cycle, but it could heal again and can withstand up to 8 load cycles before it breaks. So the conclusions of this work is that the introduction of a defect lowers the strain for plastic initiation and rupture for monotonic loading, and also lowers the resistance to fatigue failure. An increase in temperature led to earlier plastic initiation and lower resistance to fatigue failure. For some cases, we could reach some kind of steady state where nothing more happened in the material, but for some cases, this was never obtained. Least resistant to plastic initiation was the case of a void, and least resistance to fatigue failure was the case of an edge defect, but these two were quite closely matched. Thank you.
Thank you very much. 1 minute for questions. Have you any question? Yes, please.
If a dislocation were present in your beam from the initial state,
I'm sorry, I didn't hear.
if a dislocation were present, it would behave totally different. Right? You have a poor material without any defect in the initial state, no dislocation.
No, not to start with.
Yeah.
And I have no grain boundary, so you see these slips
Yeah,
right away. So
and how would the behavior change if you would insert one dislocation?
Yes, probably, but it would probably go to the edge directly to form a slip step, because I have no grain bounds, nothing to stop it from remaining in the middle. But of course it could change.
Yeah. And the second question, what determines fracture? It's just like atomic bonding. What determines fracture in your model?
I'm sorry.
What determines fracture?
No, there is no specific law for fracture. It's just the interatomic potential. So the interaction between atoms depends on the distance between them and the surrounding. So.
Thank you. Thank you very much, Mr. Hansen.